Okay, so I will talk about the data management and it will be a showcase on how we have used it within IBISBA. So I'm also part of one of these infrastructure nodes, which is Unlock, which is a focus on the microbial potential. So the topics I want to address are related to data management. There are some obvious ones. Why is data management important in infrastructure? But also to show how does it support the goals of IBISBA, and also to move on to the next level with respect to artificial intelligence, digital twins, Industry 4.0 concepts. So this where you continue to have these continuous data streams. So there have been a lot of presentations about data management in general, but how do you actually do it? So let's first start with some very open door statements. So why is data management important in infrastructure? Of course, data unlocks the secrets just beyond the surface of a research project. Without data, it becomes very difficult to perform research. But it's also to do it efficiently. So you can, of course, generate tons of data, but that does not mean that you can still answer the right questions. That you are able to validate your research. So that also by redoing experiments or by analyzing, or let someone else analyze your data, that you can come up to solid conclusions. Also, for example, if you want to accelerate your research, you want to go into for the industry, they often work with patents, you need to be able to defend them. So you need to have additional information about this. And if your data management is not properly organized, it can be sometimes very difficult to do that. Also, to assign credit to the lab members, and with lab you can have a wet lab, but you can also have a computational lab. So these are still people that are part of the research, and that you can then say, okay, this part of the analysis was done by this person, or this was done by that person. So you can actually credit the people that have been contributing to it. What is also sometimes very important is the contractual requirements. So when you do research for a group, you often agree upon a certain contract. So you need to be able to match these requirements. And in academia, what is often very important is that also other people, so you can make your data public, but then to allow other researchers reproduce your data or use your data for other kinds of research. But if there's any metadata lacking, it becomes very difficult to actually use your data sets. So in summary, everybody knows it's important. Not everybody knows how to do it. It's sometimes, if there's no proper infrastructure in place, it can become very difficult. So not everybody has the means to be able to do it properly. So you either need to do an investment, or you need to have partners where you can actually do these kind of things. And actually what happens a lot is, I will do it tomorrow, or I will do it next week. And there's no incentive to do it today, to do it right now when doing the experiments. And these are steps we are in IBISBA, we also that are taking place to really push this forward, that you can record all this information while doing these experiments. So how does this in general support IBISBA's goals? So a key statement on the IBISBA website, so we try to simplify access to advanced multidisciplinary service that can accelerate research. And to do these kind of things, you often have these different nodes with their own multidisciplinary services, and they need to be able to access each other's resources, because in one node you might have the computational experience for data crunching, another node might have the modeling or statistics experience, and somewhere else they actually generate the data. And so you need to be able to interconnect these different nodes easily and with each other. And of course, what is very important there is, of course, the data management. So within artificial intelligence, digital twins and Industry 4.0 concepts, besides normal research, they're all data-driven concepts. And without data, these topics are dead on arrival. I mean, if you have no, especially for example, for digital twins, or that need to be continuously fed with new information, if you do perturbations, what is happening, if these data streams are not up to par and you have a turnover of a year for a new data set arrives, then these become very difficult to develop and to actually learn something from. So this really requires that your data can be findable, so using API searches, that your computer can find the right data. Whether it has access or not, that's a different discussion. That's the accessible part. Is this compute node allowed to access the data to be able to transfer the information? And then once you have the data, does it have any clue what kind of data files you're looking at, what kind of format, what kind of information is in there? And also to be able to reuse them, you need to have metadata-rich information. When was this sample taken? What kind of sample is this? What experiment did it belong to it? For what study was this sample for? So all this additional metadata information is extremely important, that this is recorded properly under standardized ways, to be able to reuse it for yourself. That's the most important part, that you can yourself as a researcher can use this kind of information more efficiently, but also if you are collaborating with others, that you can exchange this information more seamlessly. So we all know this, but then of course the crux of the matter is, how do we do it? So here's an example of the of a transnational access project where we try to understand and decipher the mechanisms of a co-culture, a combination of a fungi and a bacterial member. So I will not go into the nitty-gritty detail of the expression patterns and the pathways that were involved, but just purely on a data management level, how do we move forward from this? So within Unlock, we have different facilities which can do experiments. We have a central node for the computational work. These are already highly interconnected. But for example, with this transnational access project, the experiments were actually done abroad, and we were connected through the internet to acquire the information and the data to only do the computational research. So it always starts with an experimental design. If you do not have a proper experimental design at the start of a project or at the start of your experiment, it becomes very difficult to track and trace what have you been doing, how did you do it, and what needs to be done. So we use a extended version of the ISO structure in IBISBA. So we have project information. So this is then a TNA project. What is the general project about? What are you going to investigate? Do you have one research question? Or do you have multitude of questions? There we also can set credential information, and then into more specifics. What are you exactly studying? So in this case, the co-culture transcriptomics variation between a fungi and a bacteria. And then we have the observation units. These are, in this case, bioreactors, but they can also be patients. They can be different fields you're sampling. So in this case, we had a set of bioreactors where samples were taken from, and from these samples, there was sequence data generated that we can then use for downstream analysis. So when you have a first draft of your experimental design, we work according to the FAIR by design principles. So we immediately try to nail down everything that is needed. So what is the metadata template? What kind of variables are you going to measure? What kind of conditions are you going to test? And we record this all in an Excel file, guided by a metadata system, where we can register the entire process, continuously update this metadata, and also do inconsistency checks. So if you fill in metadata and you fill in something about the temperature, we have a specific format to write down how to write down temperature, because people tend to write these things down in many different ways. So this needs to be continuously checked using this validation. And once we have done these experiments, or once the first data sets are appearing, we can immediately build up the data repository, including this metadata, which then immediately can kickstart the computational workflows. So this is then an example. So we first use a website where we can select what kind of observation are you going to do? Are you going to observe plants, animals, bioreactors? Are you taking, what kind of samples are you taking? Because these different samples require different kind of metadata. And then we can then start filling in all this information. This is often done by the researcher itself while they're doing experiments. So for example, if they start measuring the concentration when they do the preparation of the sample for sequencing, we can immediately record for the samples, okay, what were the concentrations? And then this might be very important later. If you see a sample appearing, this was of relatively low quality, we got barely any data from it. We can see, oh, in this case, this sample had very low amount of expression data of RNA available, so that might make sense. So then we can more easily find out why things might go wrong, or if we see something interesting or something strange, we can easily capture the metadata with it and then visualize it. Of course, in the backend of these Excel files, we have this metadata sheet where we can really express, if you do, for example, sequencing, you have to fill in what instrument model you're going to use, which is a mandatory field. And then we have a list of sequence equipment you can select from. This is managed by the European Bioinformatics Institute, EBI. So if you type in 454, we say this is not a correct value. It needs to be either 454 GS, GS20. So you have to adhere to certain standards. So this really helps with standardizing all your research that are being performed. And then yeah, you can just upload the Excel file for validation, and then it either gives you warnings, errors, or it will succeed. In this case, everything looks fine, except that the identifier of this specific project was used as an investigation, as a study, which is fine, but it's just that is a warning that is being represented. So in this case, we can have different levels saying, okay, this is still acceptable, but we prefer to have it differently. Or if certain values are incorrect, it will complain and saying, well, how you wrote down temperature is not correct. It needs to be in this format, so please correct your information. And this can be done by the researcher itself. So there's no push on the data steward that needs to, in the end, manage all these data streams. So the researcher can do this completely on his own. And then once it's completely past the system, then it goes to our data steward, who will then do a last check to see if everything is correct. And then we can push it immediately into our data infrastructure. So we have a landing zone in our data infrastructure. We have a landing zone for raw data, and the project structure is driven by metadata. So here, for example, we have a whole list of observation units. These are all different bioreactors under different conditions. And then, for example, observation, SAWB1, which is of course not really understandable what it means, but with the metadata, there are the more human readable descriptions. There was a sample taken of which metatranscriptomics was done, and we have one data file, two data files, one data set from that with additional metadata about this particular assay. And this is fully an automated procedure. This is all based on the Excel file. The structure is created, user accounts are coupled to it, and the files are located at placed in the right location. And because of this procedure, we can then start working on the analysis. So we have our IRODS infrastructure. That's what we use for our data storage. There we can easily store petabytes of information. We have archives in there, rule systems. So we can very easily manage all this information from all these different projects that are being executed. And then based on the metadata, we can then say, oh, this data set is a transcriptomics data set. It needs to be mapped against this and this organism. Please start this workflow with these parameters. So we use the common workflow language in a virtual environment where we can very easily then execute, in this case, 30 plus computational workflows. So this really speeds up the process. So once you've designed a proper workflow, such as this is for example, for quality analysis, we can once it's there, we can just keep reusing it and reusing it. So this really puts the emphasis on data management, but also on computational standardization. So all these workflows that we develop, we also push them into the Workflow Hub, which is a registry, which is actually based on the SEEK system that's also used by the IBISBA Hub, where we actually can share all these workflows with external partners if they want to either see what have we been doing. This is also available still in the computational workflow, but then in 5 years from now, we can still find out, oh yeah, this tool was used with these parameters, with these input files. So all this information will remain available for at least the next 10 years, as is agreed upon during these projects. And then we can easily push them into our compute analysis. So here I started quickly 4 jobs to see how everything is going. And then we see, okay, everything runs smoothly. We can just start the rest and then it will go autonomously. And then the next day we will get our results. So part of these workflows is, of course, the quality reporting. So you can have a more user interface on, it can easily check the files. It can see, okay, does this make sense that I have these bacteria and fungi in there? And that really helps with speeding up. Okay, initially this looks all okay. Okay, let's move on. And now let's dive into the expression patterns, the pathways to see everything what's happening in there. Then, of course, we still have this on our iRods instance. And then we have developed a coupling mechanism with the hub infrastructure where we can synchronize all our project investigation study assay structure, which is also used in IBISBA. To push this directly into the hub. And this is actually all the metadata that was recorded in the Excel file at the beginning of the project. So you see everything continuously comes back and becomes visible at different locations. So this really helps in guiding and in setting up all these systems more automatically. So to come back to the digital twins, the AI in the bioindustry. So if you want to implement these kind of aspects, it is key that you have machine-machine interactions because you try to reduce the user level as much as possible. You can have for example, a very basic digital twin, which is a dashboard that reports all the measurements, all the sensor information that you have, but it can also be more advanced and that it makes decisions on its own. But then it needs to be able to automatically find the new data files, know what kind of standards is being used, know what workflows to execute, to do this in a more autonomous way. You can also have, for example, bioreactor sensors that we are currently exploring with InfluxDB, that you get continuously every 30 seconds, you get input about the status of your bioreactor. What is the current temperature, your oxygen levels. So all this information is then being submitted through a broker and then stored in time series databases. So you can live track how your equipment is doing. But this is, of course, only possible through these standardized procedures. So in Unlock, we use the iRods open source data management software, which really helps us to virtualize our data store. I mean, our data is stored in Amsterdam, but you don't notice if it's on campus, in the building, or abroad through proper interface and connections. It allows for secure collaborations, this automation of these workflows, and also the communication between compute and storage. So we have our compute nodes somewhere else, and they need to be able to communicate with the data store, and that's in a completely different city. But also the communication between a measurement device and the long-term storage. These things need to be continuously and in sync. So these are very important aspects. If you want to move forward into these kind of fields, these are really the bare minimum that are needed to have this properly entwined. So of course, I was not doing this all by myself. So on the Unlock side, we have Peter and Bart. Peter is the coordinator of this platform, and me together with Bart. Bart is our data steward. We ensure that all these projects are ingested, the workflows are there, that we use the right workflows for the right experimental data sets. And the integration with Seek was developed by Alan Williams from Manchester. And the experimental project that I've just shown was together with Ludovic Bizarri from Reims. And also just to mention all the software and tools that you've seen in this website. That's the Excel validator, the workflows that we've used, the iRods machinery, the entire folder creation. These are all for part developed by us, but all software and tools are open source and free to use. So if you want to set up your own copy of, for example, the FADOM hub, the IBISBA hub infrastructure, the metadata users, these data management infrastructures, you can easily plug and play these systems into your own facilities.